Okay, thank you, Saddam. I wanted to enable my camera, but it seems that it's not allowing me. I just would like to thank Dr. Razi for accepting our invite to give this exciting talk for today. And thanks to Dr. Mohammed Khalid also for inviting you here. And we hope that we get more talks from this amazing work that you guys have been doing. I don't want to ruin the introduction, so I'll hand it over to Dr. Mohammed Khalid, and he will take the moderation of that session. Thank you very much.
Thank you.
Okay, thank you very much, Dr. Mothas. First of all, good afternoon, and for Dr. Adil, it's good night because I think 11 p.m. Midnight. So, Dr. Adil, good night, and all attendees, good afternoon, and assalamu alaikum. I am actually very excited to welcome Dr. Adil Razi, Associate Professor from Monash University, Australia. And also, I'm very excited to welcome all attendees here for this session. And very briefly, I have to say a few words for Dr. Adil. And before that, I have obviously, I'm very thankful to Sadaya and also KICS KFUPM for organizing this seminar, and also giving me opportunity to invite the distinguished researchers from Australia like Dr. Adil. And I hope that we'll enjoy this session and it will be very fruitful. So Dr. Adil is an associate professor at the Turner Institute for Brain and Mental Health at Monash University, Australia. So he joined Monash after finishing his postdoctoral studies in 2018 at the Wellcome Center for Human Neuroimaging, UCL, UK. Then he started working in the same center, and obviously he has some introduction for his lab in Monash University. So before wasting time, I can invite Dr. Adil Razi to go ahead, and he can obviously will explain his activities in his lab. Thank you very much, Adil, and now you can start your presentation. Thank you.
Thanks a lot, Dr. Mutaz and Dr. Khalid, for the invitation. It's my pleasure to be speaking to you. I hope my slides, you can already see them and it's clear.
Yes,
and you can hear me as well. Okay, great.
Yes,
okay, okay, that's great. Okay, thank you. So let's start. As Dr. Khalid was saying, my name is Adil Razi, and I am Associate Professor and heading a computational neuroscience lab at the Turner Institute for Brain and Mental Health at Monash University, which is in Melbourne, Australia. So what I'm going to talk about is some of the recent work that we have been doing in our lab in collaboration with industrial partners, cortical labs, and this is basically what I'm going to talk about is a new way of doing computations, which is to use biological neurons and use their power for computation. So first of all, a bit of an introduction. So what I do and what my lab do is what is an emerging area of field, which is at the intersection of neuroscience and AI. And this is called neuro AI. It's extremely new, where we are using so we are using how the understanding of how the brain works, and then using that understanding to build better artificial systems. What I'm going to talk about today is on the topic. Some of the main things in this work is I will talk about generative models, what the generative models are, and give an example of that. We talk about inference and how to model dynamics of an environment. So what do? We investigate models of biological and artificial neural networks, as I was saying. And how do we do that? We use neuroimaging. So neuroimaging is a way to image the brain using various different techniques, some of them non-invasive like functional MRI, and diffusion MRI and structural MRI and electric encephalography, which is called EEG. And also I will today talk about some stem cell imaging as well. We use machine learning and artificial intelligence in our work. Especially we use Bayesian inference, and that's very important. I will talk a bit more about that as well. And we use theoretical ideas from dynamical systems theory. So this is more physics or control, and you will see some of this in action. This is basically what we are trying to do in a nutshell in my lab, which is a computational neuroscience lab. Okay, so let's start with the agenda. So I will just give some introduction to what today's talk will be. So I will provide some context, some background to what we are doing, and then I will talk about something what we call free energy principle or active inference, and this is basically the main new idea. And I will then showcase our work on DishBrain, which is the world's first neural computation device. Okay, so let's start with some introduction. So as we know, the world that we are living in, we have increasing computational demands. As you could see, let me get my pointer. Okay, so that it's okay. So here's my pointer. So this is a schematic taken from a paper which was very recent in 2022 in Nature, which shows the increase in the computational power in petaflops, and as you could see, that the computational demands of these different sort of computational models is increasing about every 6 months until 2012. And many of you would remember 2012 as a time when when deep learning took off, right? So until 2012, the computational demands were increasing, but only increasing every 24 months. However, more recently now, this demand has taken off like this, and you could see things like very recent, which is like AlphaZero, AlphaGo 0, now GPT-3. All these computational powers are now almost increasing every 2 months. So what does it mean? It means that we need we need almost doubling of these every 2 months, how much computation power we need. Now, on this graph, what we are showing is the hardware development which is happening. So as you could see, from 2016 to 2021, improvements in AI hardware efficiency over the past 5 years. The state-of-the-art solutions have driven increase in computing efficiency of more than 300 times. Yeah, you could see this scale is on logarithmic scale, and the solutions in research and development promise further improvement. So it's increasing, but we need more of that. Yeah. But at the same time, there's an increase in the cost of training these AI models. So like GPT-3 or the foundational models, they have billions or trillions of model parameters, and training them is expensive. Yeah, so that's what we are showing here. You know, again, things like AlphaFold, you know, here on the y-axis is the amount of money that requires. So this is also increasing, right? So what we are seeing, increase in computational demand, increase in computational hardware or AI hardwares, and also what we see is the increase in the yeah. So is it a old message about my slides are frozen? Are my slides okay? Can you see them?
Yes, we can. But,
okay, yeah. Is it moving?
Yes, sir.
Can you see? Okay, that's fine. Okay, so what we are seeing now here is IEEE International Roadmap for Devices and Systems. Now, this is what it is showing is it is the size of the transistors, which is also shrinking. So you could see in early 2000s, we were talking about 9 nanometer technologies, or even in micrometer technologies. And now where we are going is this, where the CMOS technology is going to it's really is hitting its limits, where the transistor lengths are going to a couple of nanometer scale. Yeah, so this is what we are showing here, is just that the silicon-based computing is going towards is saturating. Yeah, so it is not clear right now that where this computational power is going to come from. Okay, so now in order to speed up the computing capacity, there is something what we call neuromorphic computing. Some of you may know this. So there is what we call a von Neumann architecture, which is the usual silicon computing that I have been talking about. And this requires sequential process. This, it has a CPU, there's an binary input and binary output, and it is based on sequential processing. And there's a separate computation and memory modules based on binary data and so on, and there is synchronous computation. Compared to this, it's a neuromorphic architecture, which is based on which is inspired by how the brain does things. So this is basically instead of sequential, it is massively parallel processing. The input are spike inputs and outputs are also spikes rather than binary inputs. The memory and processing is co-located, and it is asynchronous or event-driven computing. So this is basically a comparison between the silicon computing and what we call neuromorphic architectures, which are also based on silicons, but the architecture is different. So remember this is neuromorphic computing is also silicon based. Yeah, I'm trying to build this argument around the silicon based computing, and I will go towards biological neural networks in the next few slides. So what these artificial neural networks look like. So many of you know them very well. An artificial neuron is basically nothing but something which is based on a summation block and a nonlinear block, and it takes lots of inputs like these, and then it gives you an output. So basically, you get something what we call a sigmoid function or a nonlinear function, where you have this input which has this sort of an input-output relationship. This is basically and this nonlinearity doesn't have to be sigmoid function. It could be inverse tangent function or whatever, or some sort of a nonlinearity. So this is very simple architecture, and this is a single neuron, right? And you can actually, if you want, you can build this in hardware using a very simple, operational amplifier architecture, if you like. Now, this artificial neuron itself is very basic. However, once you add them together, so here each round is an artificial neural network, and once you stack many of them together, some of them as an input layer, some of them as an output layer, and some of them as a hidden layer, they can become a very powerful way to model for classification problems and so on. This is basically what we knew from mid 1980s to until 2010 or something like that. Yeah. Then recently, in past 10 years, deep learning has arrived, and deep learning is just nothing but very similar to usual neural networks, but now it has many more hidden layers. So instead of having one layer, there, for example, in this one, I'm showing you three hidden layers. Now, each layer has a certain function. For example, first layer will identify edges, second layer will identify a combination of edges and identify features and so on. So if you give it an input of George Washington, you will get in the end output, which is George, which says George. Yeah. So this is a very well-known deep learning neural architectures. Now, compare this to biological and artificial networks. So, for example, we take a example of a brain system of an actual human brain, and we can then measure activity in different parts of the brain. So this is what my lab does, where we actually take actual brains and measure activity in different parts of the brain. So different parts of the brain, like frontal areas, occipital areas, and so on. And then you can use this activity to create these similarity matrices of functional brain networks. So you can see each node or each dot here is a brain region. And then basically using these time series or activity, you can actually create something like a brain network. Just like, you have a social network or a mobile network, you can actually build brain networks. Now you can model these brain networks using either artificial dynamics, where you can actually use the artificial neural network, just like I was showing you. So you can use an artificial neural network with lots of inputs, and you can have an input to this, for example, in this case, a dog, and then it will classify it as a dog. On the other hand, if we are working with the actual brains, then you can model these brain dynamics at various different at various different scales. For example, at a very fine scale, where you can model a neuron and its output, we're using for something what we call a Hodgkin-Huxley model, or you can do this modeling at a meso scale, where we can do something what we call Wilson-Cohen models, or you can do a large scale architectures that, for example, something like a functional brain networks. Now, so this is sort of a different ways or a contrast between artificial networks, where you have these artificial neurons which can do something like a classification, and here we are actually modeling actual brain systems. But the idea is this, but you can ask that while we have artificial neural networks and they do very well, then why do we bother about biological networks and what function they serve, right? Why they can be useful. So let me just quickly go through this. So this is basically what I'm showing you is an inverse pyramid of innovation in AI. So for example, we start with theory. So there is a theoretical background to deep learning, right? So there is very, which is not which is not easy, but there is theory, right? Usually people think of deep neural network or AI as a black box, but there is some theoretical underpinning pinnings to it. However, very few people work on the theory side. Most people will use these neural networks to solve technical problems, for example, in image recognition or image segmentation or natural language processing things and so on. And from this, people make industrial applications, for example, autonomous cars and all that. However, the issue currently is this, that the current neural network or artificial neural network field is basically is actually solving problems that humans do unconsciously. So, for example, classifying, looking at different images and telling them it is a dog or a cat, right? So for this, humans don't need a lot of computational, they don't need to think a lot. They can just solve these things unconsciously. Or even like, for example, if you are shown an MRI image of a stroke of a patient, if there is a very trained physician, they will not require a lot of effort to just say that, okay, what kind of tumor it is, how severe it is, and so on. However, this is what the current artificial neural networks look like. All the work that's happening in AI and deep learning is basically solving very small kind of problems. Although more recently we have a bit more, but this is what's actually happening. What is the future? I mean, in future, we want to solve problems which are based on reasoning, for example, and planning and things like these. Like if you want to plan your next holiday, there's lots of planning happens, and how do you do that, right? So this is a very conscious kind of processing, and current neural networks, they are not able to solve that. And what we think that we require, we will require something like biological neural network, or at least artificial networks which are mimicking biological function more closely. So let me show you an example of a biological neuron. So compare this with artificial neural network that I showed you in previous slides, which is very simple summation and nonlinearity, while a biological neuron itself is a very complicated biological structure. It has many different parts, mainly a body, some dendrites and axons and many other things in this, right? So it's a very complicated thing, right? It's just not like taking an input and giving you an output and having a nonlinearity. It does a lot more than that. It has, in a sense, has memory and all that as well integrated into it. So if we can, the idea here is this, can we use the power of a biological neuron to do computations? Okay, so what is the scale of neural computation? I told you, I showed you some of the scales of computation that we're doing for neural networks or artificial neural networks. Now, compare this with this. In a usual human brain, there are about 10 to 100 billion neurons. Yeah, so every brain has this many neurons. And then each neuron has about around 10,000 synapses. So what we usually say is this, that if we take all the neurons and the synapses and join them together, the amount of wiring is enough to go from the earth to the moon and come back. So that's the amount of wiring which is actually present in a human brain. Yeah, so that's the amount of computation one can do, one has packed into the brains. So there are about 10 raised to power 13 computing elements, right? So that's a several more magnitudes more than the most advanced artificial neural network can have. So what I'm showing you is Raman Kyle. Raman Kyle was a very a very famous neuroscientist, and these are the drawings of the hand-made drawings on original work where he has drawn neurons and the cortical sheets in which the neurons are organized. So what I'm trying to tell here is that the biological neurons are extremely cheap, and they are what I have not here is this, that they're also in terms of the energy very in terms of the energy, they're also very conservative. So, and a human brain only requires 10 watt of energy to operate. Compare this to large AI systems, which would require gigawatts of energy to train them. Yeah. So compare the human brain, how small it is, but how much power it has compared to huge artificial neural networks, which cannot do things that the human brain can do, but they require large amount of money in terms of training them and energy, the requirements and all that they have. Okay, so that's sort of an introduction to the so let's next go to something a new theory, not really new. It's been there for a while now, but maybe it may be new to several of you or for several of you today. So what we are trying to do is with this theoretical framework, this is what we call active inference. We are building a new sort of machine learning, a new sort of AI. Yeah, and that's why we call this a new era of AI. So one of the central questions is this, that how agents like us, like humans, operate in a given environment. So for example, in finance, we make decisions about buying and selling shares, for example. Yeah. How do we perceive and respond actively, optimally, for example, in a very volatile share market, right? So this is how humans operate and succeed. Yeah. Or for example, a kingfisher, which is a which catches a fish, right? So this is an example of a fish, of a kingfisher, which is a bird and catches fish, right? And to do this, to survive, they have to do a very complicated procedure, right? They have to time their dive so that they can catch the fish before it goes deep into the water. Yeah, so that's a lot of movement and timing that they have to have. So how do we, and then the waves are coming and all that, right? So it's a very dynamic environment, but then still these birds can catch their prey to survive, right? So what is this? So this basically, the question is how this intelligence emerge with time? How this with a for example, an infant, initially, would not have a lot of intelligence, but they become adaptive and they become intelligent over time. So how this intelligence and high performing ability comes from? For example, a parrot which is looking at this very simple puzzle, while a kingfisher can do much more complex things very easily. So how this intelligence emerges over time? So is there a unifying theory? So is there a unifying theory for behavior intelligence? For this, for example, there have been quite a few computing theories in literature. For example, reinforcement learning. Some of you may have seen seen this. It's very powerful, reinforcement learning, but still it has lots of limitations. Game theory, several Nobel Prizes have been given to this. Many of you have seen the movie The Beautiful Mind, in which the basics of principles of game theory were the biography of this where how the game theory and cooperation and coordination framework emerges. Principle of economics, and economics, there are theories which try to explain these uncertain. So basically what we are saying, so all these mathematical frameworks are there, and they all try to find some sort of a optimal solution to very complex problems. And most of the time these they are suboptimal. These solutions are suboptimal. Usually they fail when there's a lots of uncertainty in observations, and so on. So is there a, however, I mean, it seems that there must be somewhere some unifying model which would be able to solve things optimally, because we see that in nature and in biological systems, they can do this very efficiently. So one candidate is what we call the active inference, or what we also call the free energy principle. So what is active inference and free energy principle? So it is basically nothing but a biologically plausible mathematical framework which emerged in neuroscience as a general theory of behavior. So and what it is, it basically tells that that an agent, which could be a human or an animal or a cell system like what I am showing you on the screen, it maintains homeostasis by residing in attracting sets that minimizes entropy. So this is basically a very simple definition of what the active inference is, that what we do in order to survive, we try to remain in few states such that we try to minimize entropy or the surprise. So, as a human, for example, we only reside in few states, like either we are sleeping or we are waking, or eating or running, or, there are few things that we do. We do go in a cycle, right? In the morning, we get up, we go to work, another state, we do our lunch, we take rest, then we in the evening we do some leisure work, and then we go to sleep. So there are few states that we are in, and we try to we repeat ourselves in those states. Yeah. And we do this to minimize entropy. So that's the main postulate of this. And here, and I have used another word, surprise, and there's a relationship between entropy and surprise, as I show here. There's entropy is related to surprise, where S, or surprise, is nothing but the negative of log of a probability of some outcome. So there's a P of O, which is a probability of some observation or outcome, and if we take the negative log, this is what we call the surprise. And some of you will recall this as a self-information and information theory. And as I said, what active inference is saying is this, that we try to minimize entropy. Yeah. So how do an agent like us, we minimize the surprise or the entropy? And this is one of the main questions. So what we say, according to active inference, the free energy principle, that we actually have a generative model, or a world model. Many of you probably know in machine learning, we talk about world model, right? World model is a model which every organism has, according to which we generate predictions, and we test those predictions based on what data is coming. So for example, there's an agent and they have an internal generative model. And this generative model is just nothing but a joint probability of some states and some observations, which we show it here as this, right? And then there's an agent and there's an environment, right? So we live, every agent lives in an environment, the world around us, and this environment has generative processes. Yeah, so this is very important, a distinction between an environment, an agent, or an internal states and an external state. So agent has a generative model, and environment has a generative process, and there's a transaction between an environment and an agent, and this is basically how this framework is motivated. As I said, what we do is this, that we need to minimize the negative log of this quantity, or the surprise, which we call surprise. So if I want to calculate what the probability of an outcome is, which is P of O, yeah, we can write it down as a summation of this joint probability. However, in most cases, solving this, calculating these summations or integrals is impossible, because the parameter space is huge, or indefinite, is infinitely large. So we cannot solve these problems analytically. So what do we do is, usually if we take a negative log of this, and this is what we call the surprise, and we write it down as something like this. Yeah, so this is basically what we call we cannot solve this thing, but we can solve an upper bound on this. This is what we call the surprise of the free energy, and where Q of S is a sample sample distribution, or the target distribution. So here we call this thing as a free energy. So this is basically nothing but a lower bound on the surprise, and we can write it down as so this is the only slide where I have some maths, and then I will move on to I will not use any more maths. So basically, this is important because we need to know what the free energy is and active inference is, and for this we need to have a mathematical relationships. And here I define free energy as a complexity and accuracy term. Without going into the maths of this, you can just think of free energy or the surprise as a quantity which has complexity and accuracy. And what I'm saying is this, that that any agent, including us as a biological agent, we survive by minimizing this quantity. Basically, what I'm saying is this, that we try to find the balance between the model complexity and its accuracy, or trying to find out the most accurate explanation of data, which is the simplest. So, or we can write it down as an energy term and entropy term. That's another formulation of the same thing. So what I'm trying to say is this, that here that active inference requires finding out lower bound, which is what we call free energy, and minimizing this bound, and this will result in an optimal decision making. Yeah, and this is what the biological agents do. Okay, so that's a bit of a introduction to active inference and free energy principle. Now I want to show you how do we use these very mathematical ideas to develop actual systems which can beat the best of AI systems. Okay, so for this, I'm now going to the more experimental part, or the more exciting part of today's talk, which is to talk about something which we call DishBrain. DishBrain is a system which is capable of synthetic biological intelligence. Basically, what we are doing is to harness the power of biological neurons to do goal-directed tasks. So the question is, can we harness the computational capacity or capability of biological neurons for artificial intelligence? And does biological agents use active inference? So there are a couple of questions. First of all, can we use the power of biological neurons so that they can do things for us, like solving difficult problems? And an important and theoretical question is that is the active inference is used by the biological agents. So in order to test this and then to see if we can do this, can we harness the power of biological neurons together with a startup called Cortical Labs? We have set up a high throughput biological workflow where we have actually cultured neurons, two different sort of cultured neurons. One is derived from humans and others which are from rodents or mouse. And then we are using these cultured neurons and put them in and use them to do some useful tasks using active inference. And the overall goal is this: can we develop more faster and cheaper AI chips which are made up of biological neural networks rather than artificial neural networks? Okay, so so here it is. So how this whole system looks like. This system is, first of all, is the first real-time in vitro demonstration of synthetic biological neurons which are coupled to a virtual world. We demonstrate that using this system, the neural cells or the neurons engage in adaptive behavior. That is an emergent property of engaging with the environment. We provide the first ever evidence the neurons can self-organize in vitro. And we use this to do and we use this self-organization property of neurons to do useful tasks. So basically, what we have here is this: there's a high definition multi-electrode array chip on which we have either plated the human neurons or mouse neurons, and then we have put the whole thing in the simulated game world, and we have shown that these cultured neurons will play a game of Pong and get better at it. And we show that they display this intelligent and sentient behavior by playing the game of Pong. So this was many of you might have seen this work, which was widely covered by almost every large media outlet in the world, including Nature, BBC, CNN, Economist, etc. So what is this setup? How it looks like? So what we do, either we use stem cell technology to differentiate human cultured cells This is a very elaborate process, or we use mouse neurons or rodent neurons, primary cell cultures from neurons. Then we put these neurons when they are matured onto a high definition multi-electrode array chip. We plant this. These cultured neurons on top of this chip, and then we develop a real-time closed-loop system and show that these neurons can play the game of Pong. Pong is a very traditional arcade game where it's a single-player game where there's a ball which is deflected from the wall, and there's a paddle which is moving and trying to hit the ball towards the wall. So in this system, we have used a closed loop feedback system, and I'll talk about it quite a lot in next few slides. I will quickly go through this because this is more on the cell biology side. I don't think that there would be a lot of interest in those slides, but still I will show quickly. So what we have is this, that these are differentiated. The one on the top are the rodent cultures or mouse cells, and these are the one on towards the bottom, they are the human cells. Here the blue ones, they show all different kind of cells, the blue ones, and then these green ones, as they call neon or neon, these are the cortical neurons shown in green color. We have this one, the purple or the pink ones, they are the axons, which is the body of the neurons. This purple one, they are the dendrites. So dendrites are the another structure on neuron which connects with other neurons to communicate. So this is and then we have all of them here shown together. Blue ones, they are all neurons. Greens, as I said, cortical neurons. Then pink ones are the axons, and then purple ones are the dendrites. These are the images which are imaged after 80 days of maturation. Here we have about in these neurons we have glial cell as well, which are shown as here. These are non-neuronal cells, very important for long-term function in our brains. We also show that they are the brain is hierarchically organized, so we have cortical layers 2 and 4 neurons in this as well. Here we have used here we have these neurons, which I was showing you in the previous slide, and then they are plated on a high definition multi-electrode array chip. So you can see these are neurons here, and the pink one at the back, or at the back, they are the sensors or the MES surface. These images are taken using cryoscanning electron microscopy, very high definition images that we have shown. These cultures can survive for more than 6 months once plated on an MES surface and properly provided nutrients. There are some inconsistencies and problems, but I won't go into that. So this is basically neurons on a chip. Here we show these are rodent neurons and human neurons. We show quite a lot of firing. That yellow thing, it means these are functionally active, and different frequencies are shown of spiking. So these are mouse neurons which get matured after about 2 to 3 weeks, while the human neurons, they take about 3 months to about 3 months to mature. So how do we teach these neurons to play games? For this, the main thing is that these neurons are embodied, and the embodiment is achieved by putting them in a closed loop feedback system. So what I'm saying is that the usual, like living organisms, they require closed loop feedback to operate. So like us, like we require a closed loop feedback. So we live in a world and we are all the time we are getting feedback from our environment. We take actions, we change around things around us, and then we sense the changes, and then this whole loop goes on. The closed loop feedback involves the stimulation, sensation, measuring responses, through our senses, for example, with eyes, ears, and nose, for example, then providing sensory feedback on how that response impacted the world by altering the sensation. So here we are simulating the sensation and sensory feedback by using a closed loop feedback system, which is basically the main patents for this work are in the real-time implementation of this system. The setup looks like this. So as I said, there is a MES surface, microelectrode array surface, on which you could see these blue ones. There are the neurons. There is firing which is happening. There's an output which is basically we are recording by using by using the MES surface. We provide a stimulation by using the feedback system, and so on. So we provide structured information, which is stimulation, to represent ball position in a real-time closed loop environment. And because of this closed loop environment, the ball, the neurons learn to play how to return the ball and learn the ball-pedal relationship. So here's a quick video of the system, so you can see that this is a visualization. Yeah, so I will just let you see this. Okay, so that's the video where I showed you a simulation of how the neurons are playing the game of Pong. What we are, maybe I will just, because of time, I will just go and show this slide. So what we are doing here is what I'm showing you here is this, that so each session of gameplay is about 20 minutes. So the neural cultures, they are playing the game for 20 minutes. And then we compare the rally length in the first 5 minutes with the rally length in the next 15 minutes. And as the neurons learn over time, the rally lengths are longer, right? So which means they are hitting the ball more often. So here, average rally length, the green one is the gameplay in the first 5 minutes, and the orange bars are the next 15 minutes. So there are 3 different controls. So CTL, IS, and RST, we don't need to worry about what exactly they are. They are just control conditions. And you could see that in the control conditions, there is almost no learning, in these 3 conditions. And then important one is these MCC and HCC. MCC is the mouse cortical cultures, and HCC is the human cortical cultures. And what we are showing here is this, that mouse cultures have some learning. So you could say, you could see that the average rally length is now higher, and it is significantly, we have done t-tests, and you could we show that there's a statistically significant increase, and we show that in human neurons the learning is the highest. Yeah, the rally length is highest in the in the later 15 minutes of gameplay. If we compare, the rally length is significantly higher in the first 5 minutes, and there are a few other things like aces and long rallies and so on. So what we are basically showing is this, that these human neural cultures and also mouse cultures, they are showing learning over time, and we have shown that we can actually use the capacity of these biological neurons, put them on a chip, and then they can show, we can make them do things. Yeah, I don't need to go into, I will just conclude. What I have shown here is this, that the DishBrain system, it exhibits natural intelligence, where we have harnessed the inherent adaptive computation of neurons. While this is a very simple system, but it is the first demonstration of the capacity that we can actually harness neurons, actual neurons, and they can play games, right? And they can get better at it. So there's some questions about this. There's that, are these neurons conscious? We don't think that these neurons are conscious, but there are some debates happening on this topic. There are many ethical concerns around this as well. So we are working on that side as well. And there are many other questions that arise from this, because these systems have a lot of they have lots of implications across the technology, science and technology and philosophy and religion, and ethics and society. So it has lots of implications, because what we are saying is this, that in 30 years time, by 2050, you will actually not be using silicon computing like a laptop, which is made up of transistors. What we are saying is this, that you will be working on devices which are made up of actual neurons, and this will change everyone's how we operate in this world. So with this, I would like to thank you, lots of people in my lab, and also many international collaborators, especially our industrial partners, Cortical Labs, and many other funding agencies. With that, I would like to thank you, and happy to take any questions.
Okay, Dr. D, thank you very much for this very interesting and amazing presentation today. Actually, it opens a path towards building an AI that thinks like a human. So very interesting, very amazing. Thank you very much. Again, we have 5 minutes for questions and answers. I have one question here. The first question says that does AI has some limitations?
Of course, it has lots of limitations. AI, current artificial systems, as I said, they have lots of limitations. First of all, they require a lot of, they're expensive. Building a large language model, for example, these days, ChatGPT and all those systems, they are pre-trained, and they're trained on huge neural networks, and it requires lots of computation power. And even though they're expensive, they require lots of energy to train them, they're still pretty dumb, right? They cannot engage in a reasoning task, right? If they have, although they are getting better and better, but they don't have, for example, the causality, the causal interaction, the reasoning and planning capacity. So there's a lots of limitations, and that's why what we are proposing is a system which is completely different. So this work is basically, what we are saying is this, that instead of using artificial neurons, we use actual neurons, right? And then they have a lot of capacity. As we know, our brains are made up of them. And can we use this power to actually do the computation?
Okay, thank you, Dr. Adil. The second question, first of all, he says, Ahmed Irfan says, amazing work, and he's thanking you for your presentation. He has two questions. He says that how the neurons are providing nutrients. Can different nutrients lead to different performance? This is the first question. And the second question is that based on the experiments, did you observe major differences between rodent and human neurons? Thank you.
Okay, yeah, a very good question. So first question is that I would just go to this slide. Yes, so these neurons are put in nutrients. So these are basically sort of a liquid with lots of different vitamins and all those things. So this is a very mature field. We are not saying that this is something new that we are doing. Stem cells are created in labs or organized. They are done very regularly in both academic and research labs. Different nutrients would lead to different sort of so this is a different discussion, but important point that for example, if we are to build these systems or devices in millions or billions of such devices, where these nutrients will come from, and will we be able to have enough nutrients to build all those, if we are talking about in 30-40 years, if we're replacing silicon computers with biological computers, where these nutrients are going to come. So these are all important questions and require, this is very new. This is opening up many different questions, and one of them would be how to make these neural cultures sustain over longer period of time, and there would be more research required in that the second question was about is there a difference in the performance of mouse neurons and human neurons? So yes, this is one of the main we didn't highlight this as one of the main results of our work because it is controversial, because we also provide one of the very first evidence, I should not say very first evidence, but there's a growing evidence that human neurons, they have intrinsic advantage over other animal neurons. And this is, we are showing here, this MCC is the mouse cortical neuron cultures, and these HCC, these are, and you could see that there's a more learning, the learning rate is higher, or the learning capacity is higher in human cultures than, as you could see, this is slightly lower and this one is above. So yes, we do show that the human cortical cultures are doing more learning. This is on itself is a big result, but there are lots of other implications, and there are lots of difficulties in such research. I wouldn't go into details of this, but yeah, this is true that human cultures actually show more learning in our setup.
Okay, thank you very much, Dr. Adil. Maybe this is second last question. I think Dr. Tariq, he says that I have a question about how the parameter tuning is happening here. I mean, how exactly the brain cells are guided towards the right solution for the problem.
Yeah, that's a very important question. So I think, first of all, there are no parameters here, right? So this is not an artificial neural network where we are actually tuning the parameters of an artificial system. Of course, there is a tuning of parameters happening naturally between neurons, which is basically so there are about 800,000 neurons in this dish. So there's about 1 million neurons, and they are firing, and there's a patterns of firing which is happening, and we are looking into this as we speak. Are there specific patterns of firing which are happening when the learning is during learning phase, right? So yes, there is that's one part. The second second part is this, that how these neurons are actually going in the right direction towards learning, right? So that's very important question, very fundamental question. And the answer to this is active inference or the free energy principle. So what we are doing in this system is this, that when the neurons they miss the ball, we provide them with a random uncertain signal. So that's like a punishment, just like a slap, right? So if you miss the ball, we will give you an uncertain information. And according to free energy principle, biological systems, they don't like uncertainty. So they try to minimize the price or minimize uncertainty. So over time, when they hit the ball, we provide them with a predictable signal, and when they miss the ball, we provide them a negative reward signal. And that's basically make them learn over time based on free energy principle. And for this, the whole closed loop system is important.
Okay, thank you, Dr. Adil. I think we have a couple of questions, but I think time is over. Saddam, what do you think? Can you go for another question, or should we conclude now? Okay, so Adil, maybe if you give me just for last question, which is I think it's typed in the chat window. It's a long question. If you can just look at it very briefly and answer. It is from Ihsanullah.
Okay, yeah, I can.
Yeah,
I can try to look at that. For excellent talk. Indeed, you are doing exciting work. Please briefly touch on the architecture of the deep neural network. In addition, what is the basis for architecture? Okay, so this question is about the architecture of the deep neural network. So the main thing is this, that what I'm saying, we're not using deep learning architecture here. There's no artificial deep learning architecture here. We are using actual biological neurons. Actually, there's another question in the Q&A, the last one, which is talking about there are lots of similarities with the reinforcement learning. So I would just quickly like to answer that question, because I think that's very important. Someone has picked up that active inference and reinforcement learning has lots of similarity. That's correct. However, active inference has lots of differences with reinforcement learning as well. The first of all, in reinforcement learning, I don't think that it is biologically tenable. It is not biologically plausible because it has separate planning, perception, and learning tasks or learning phases, which means that you require multiple objective functions, while active inference has a single objective function, which is to minimize the free energy. Another difference is this, that for reinforcement learning, you need to create a reward function, and creating these reward function is not easy, and in most cases we don't have the actual reward function. In active inference or free energy principle, some of the time we actually don't need the reward function, because the policies they actually have epistemic value, or in active inference you can actually learn the reward function over time as well. So there are lots of differences, but there are similarities as well. So it's a good question. Active inference is a new framework, it's still evolving, and we don't have mathematical proofs which show unambiguously what are the differences between active inference and the reinforcement learning. But intuitively and empirically, there are multiple differences, but there are commonalities as well. So it's a good question. More to be known about that as well in future.
Okay, thank you very much, Dr. Adil. So I think we have some questions, but I would like to end this session because we are 5 minutes ahead of our scheduled time. So maybe the audience for their questions, they may contact you via email. Maybe it's the best approach. You can have a contact with Dr. Adil. Unfortunately, I'm really sorry that I cannot take all questions because we're already 6 minutes ahead of our scheduled time. So thank you very much. So at the end, on behalf of our director, Sadaya, and KFU PM, especially Kix and Sadaya, I would like to thank you, Dr. Adil, for this amazing presentation and sharing your very good, amazing work in AI. And again, big thanks to you from KFUPM and all of us. Also, I would like to thank you all attendees who attended this session very actively and for their questions. I hope that will have more sessions from you in future, inshallah. And if you have any comment, any question, anything, you can basically say, Dr. Adil.
Yeah, thank you. Thanks a lot. I mean, I really enjoyed the questions were very interesting as well. It seems there's lots of interest and the quality of questions was very high. So thanks everyone for your time and interest.
Okay, so thank you very much. So we are ending the session now, and thank you very much. And for you, Dr. Adil, good night, and for attendees, good afternoon, and enjoy your rest of the day. And thank you very much, and assalamu alaikum.
Wa alaikum assalam.